Welcome to this lecture series in linear algebra. In this lecture, we'll look at the notion of cosets of a subspace, and all we need to know is very basic things. If you're comfortable with the notion of a subspace, that should be more than sufficient to follow this lecture. So let's move on. Here are some problems for practice. And now let us get started. So fix a vector space V over some base field F. Here, for example, we have taken the vector space as R2 and fix a subspace of V. Let's say this line passing through the origin. Okay. So we want to define cosets of this subspace. Fix a vector little v. Okay. So define, this is just a notation, define v plus u as, so that's the, this is just a notation and this is what it means. So you pick a vector in U and add v to it. Pick another vector, add v to it. You do this for all the vectors in U. What you get, you name as little v plus capital U. So what does this look like? It is just translating this entire thing by the vector v. So that's what it will look like. This is v plus u. Okay, and now we can define a coset. So a subset S of v is said to be a coset of u if there is some vector v such that the subset S is v plus u. So a subset S of v is said to be a coset of u if it is a translate of u in natural language. Okay. So this is just the definition of a coset, and the set of all the cosets is denoted by this symbol. And how do we read it? We read it as v mod u. Okay. So just some definitions and notations, nothing very complicated going on. Note that if little u is in capital U, then little u plus capital U is same as capital U. Of course, this can be seen by this algebraic definition, but what is going on is if you pick something in U and you add this to all things in U, of course, you're going to recover U. Visually, this should be obvious. Okay. So that's just a very simple definition. As an exercise, you should tussle with the following. It's a very simple exercise. Suppose we define a linear map from R2 to R as, and let K be the kernel of T. Recall the kernel is all those vectors which are mapped to 0 under the transformation T. What are the cosets of K? Draw them. Alright. So now here is a very fundamental property of cosets. The set of all the cosets of any given subspace partition the entire vector space. Alright, so the statement is self-explanatory if you look at this picture. The cosets are all these lines, and of course they partition the entire R2. Everything has to lie on exactly one of these lines. Okay. So before we proceed, let me also mention that many times we will write this as V bar. So this of course suppresses the dependence on the subspace. For different subspaces, this will be different. But when there is only one subspace hanging around, it is good to just abbreviate this thing to V bar. It helps. So that is what we will do. And now, first we show that two distinct cosets are disjoint. Okay, so to do this, to do that, let V1 and V2 be two vectors such that the corresponding cosets intersect non-trivially. So we want to show that actually the cosets are the same. That is, these two things are the same. So this will show that two distinct cosets do not intersect. So we will show that. This is the case. Now since they intersect non-trivially, we can choose some vector v in their intersection. So then v can be written as v1 plus x1, and v can also be written as v2 plus x2 for some x1 and x2 in the subspace U. Why is that? Well, by definition, v bar, sorry, what have I written? This is v, I'm sorry about that. So this intersected non-trivially, so we just picked a vector in the intersection. Okay, and since v is in v1 bar, one should be able to write v as v1 plus something in u. That's the definition of v1 bar, and similarly for v2 bar. Okay, so therefore, we have v1 plus x1 equals v2 plus x2, and hence v1 is equal to v2 plus x2 minus x1. Therefore, v1 plus u is equal to plus u. But this is equal to, and this is a little bit of an exercise, very small exercise. So here things have to be understood. This is a set. v2 plus that set just means add v2 to everything in here and create another set. That's what it means. So this is equal to that is nothing. It's very simple, but has to be proven. And now since this lies in the space U, as we noted, this thing is again U. So why? x1 and x2, so here, yeah, x1 and x2 are in the space U. Therefore, their difference is also in U, and therefore this is equal to U. So this is equal to v2 plus U. So the upshot is v1 bar is equal to v2 bar. So we have shown the orange thing. And we should also show that everything is in one of the cosets, but to do that, just note that v is always in v bar. This is for all vectors. Right? This is trivial. So that shows that indeed the cosets partition the entire vector space. Okay. So here is a simple lemma about equivalence between various ways of saying the same thing. So fix a subspace of a vector space V and fix two vectors. Then the following are equivalent. First is that v1 and v2 are in the same coset of U. Second is that their difference lies in U. And the third is just a repetition of the first one. So third one is nothing new. Or well, not nothing new, but certainly this implies that. So yeah, I shouldn't just say that they are equivalent right away. We have to prove everything. So let's do it. So 1 implies 2. Why is that? So V1 and V2 are in the same coset, so there exists by 1, there exists some vector V such that both V1 and V2 lie in the corresponding coset. Okay, so therefore V1 is equal to V plus x1 and V2 is equal to V plus x2 for some x1 and x2 in the subspace. Alright, so now take the difference. So this implies V1 minus V2 is equal to x1 minus x2. Just take the difference of these two equations. So we see that this thing is of course in U because x1 and x2 are in U. So this implies 2. This implies V1 and the difference of V1 and V2 is in U, and that is 2. So 1 implies 2 has been proven. 2 implies 3. Okay, so by 2, there is x in U such that, maybe I'll change the color so that you can discern. So what's a good color? Let's use pink maybe. So by 2, V1 minus V2 is equal to x for some x in U. Alright. Therefore, V1 is equal to V2 plus x, and thus V1 plus U is equal to V2 plus x plus U, and that implies V1 plus U is equal to V2 plus x plus U. We commented on this kind of thing earlier, so I will not repeat it. We have that, but again, this is already in U, so this is U, and we get V1 plus U is equal to V2 plus U, and that is the statement of 3. Okay. Now, what about 3 implies 1? That is the easiest one. So V1 plus U is equal to V2 plus U, but V1 lies here and V2 lies here. These two cosets are the same. So V1 and V2 lie in the same coset of U. That's it. There's nothing to do here. So these three things are equivalent. It's good to remember this. Lastly, cosets can be obtained by an equivalence relation. This will be more or less an exercise for you. So the setup is the same. Let U be a vector space, a subspace of a vector space V. Define a relation tilde on V as V1 tilde V2 if and only if their difference lies in the subspace. So here is the exercise. Show that tilde is an equivalence relation and show that the cosets of U are precisely the equivalence classes under tilde. Okay. So that's all for this lecture. As usual, like, comment, share, subscribe, and I will see you next time.